Okay, well, welcome everyone to the first video in the series of videos covering Casella and Berger's classic textbook, Statistical Inference. This video will cover section 1.1, which is on set theory, and that's the first section in chapter 1 on probability theory. So you'll see each video will cover one section, and I'll also cover some of the exercises from the back that pertain to this section. In this case, I decided I would do exercise 1.3 from the back, which you will see amounts to proving theorem 114. So I'll do that part as I go along. That's about it for the intro speech. So let's get started by talking about sample spaces. So the sample space is a concept tied to an experiment, and the very first sentence in section 1.1 says, one of the main objectives of a statistician is to draw conclusions about a population of objects by conducting an experiment. So this term experiment here is not really introduced. It's kind of assumed that people already know what an experiment is. As we go along, we'll add additional color to our understanding of what an experiment is. But to start off with, I think it is sufficient to think of an experiment as the process by which a sample is obtained from a known population. So you start off with a known population, and through the process of an experiment you obtain a sample. And so this process of an experiment has to be something that is repeatable. It has to have a random component so that the outcome cannot be known ahead of time. And that's about all we need to know at this point about what an experiment is. And it is the laws of probability that will guide our thinking around what a sample from a population could look like. Now, if we were to go the other way around, and we started with a known sample in hand, and we wanted to reason back to what the population from which it was drawn might look like, that's where we'll use statistical inference. So you see that in order for us to do statistical inference, which is the title of this book, we'll need probability, and then it is no surprise that this book spends the first half on probability and the second half on statistical inference, and that's typical of all statistical inference books, because we need probability as a foundation for statistical inference. So that's kind of the big picture, and the authors introduce as the first thing, and they introduce the concept of a sample space. So I'll do the same. So what is a sample space? So the sample space is simply the set of all possible outcomes of an experiment. So if we think about the experiment of tossing a coin, then we know that heads is one possible outcome, tails is the only other possible outcome, and if we put these outcomes, which are all the possible outcomes of this experiment, in a set denoted by capital S, this is the sample space of this experiment. And I might number this experiment as 1A. And then for 1B, let's think about what the sample space of an experiment in which we would toss a coin 2 times would look like. So if we're tossing a coin 2 times, then there will be 2 coin readings that will form each outcome. Heads is one possible outcome, right? So heads on the first toss and heads on the second toss. Heads, tails is another one. Tails, heads, and we're just missing tails, tails. That's it for 4 possible outcomes. We'll put these possible outcomes in a set and denoted by capital S, and that's the sample space of that experiment. So if we tossed a coin 2 times or tossed 2 coins at the same time, we would those are different experiments, but the sample space could be denoted the same way in both of those cases, and it consists of these 4 outcomes. Okay, let's look at another experiment, the experiment of rolling a die. So we know that when we roll a die, we have 6 possible outcomes corresponding to the numbers 1 through 6, the integers 1 through 6. Okay, that's the experiment. That's the sample space of that experiment. If we were observing the SAT math score of a randomly selected student, the sample space for that experiment consists of the set, which starts with 200 because that's the lowest possible score. SAT scores increase in increments of 10, and they go all the way to 800. So 800 is the largest possible score. Okay, so that's the experiment. That's the sample space for that experiment. If we were observing the reaction time to a certain stimulus, and if we suppose that there's always a delay, a non-zero delay between stimulus and reaction time, then the sample space will consist of numbers that exclude 0. 0 is not possible because of that delay. But the reaction may never occur, so then this waiting time can go into infinity. So we got the positive real numbers here for the sample space. Now, what if we, and this kind of it's the same experiment, but looking at it differently, observed the reaction time, but this time we the reaction time to a certain stimulus, but this time we rounded it to the nearest second. So a reaction time of, let's say, 0.1 seconds would get rounded down to 0. Okay, so now 0 becomes a possible outcome. 1 is also possible, 2, and so on. And it's still possible that the reaction may never occur, so this continues indefinitely. Okay, so we've looked at some experiments, and we looked at their corresponding sample spaces. One of the first things that we'll want to do is to be able to classify sample spaces into countable versus uncountable. So the easiest thing to do is first to see if the sample space consists of a finite set of elements, because if it does, then it's definitely countable. So let's start with that. So in 1a we have sample space that consists of 2 elements, so it's a finite set of elements, therefore sample space is countable. In 1b we've got 4 elements, is countable. Experiment 2, we have another sample space that consists of a finite set of elements, countable. 3, countable as well. And that's about it for sample spaces that contain a finite set of elements, right? So, okay, that first pass we are we're done. Let's see now how we deal with sample spaces that have an infinite number of elements. So if a sample space has an infinite number of elements, but if these elements can be put into a one-to-one correspondence with a subset of the integers, then that sample space is still countable. So notice for experiment 5, we have a sample space that consists of a subset of the integers, and therefore it can be put into a one-to-one correspondence with a subset of the integers. Therefore this one is still countable, although it has infinitely many elements. So this is a little bit kind of strange. You have to pause to see that that makes sense, but it says that yeah, you can count this one. It just goes into infinity. You can count its elements. In contrast, for experiment 4, we have a sample space that consists of the positive real numbers, and the positive real numbers cannot be put into a one-to-one correspondence with any subset of integers. Therefore, this sample space is uncountable. Okay, so so sample space is the first term we need in order to start reasoning about experiments. The next term we would need, which will expand the possibilities of what we can do in reasoning with experiments, is that of an event. Event is another very simple concept. An event is simply any subset of a sample space. Simple as that. So if we consider the experiment of rolling a die, we know the sample space consists of the numbers 1, 2, 3, 4, 5, 6. Then one event that we might be interested in might be event which we might call A, and maybe it consists of the even numbers. Another event we might be interested in, we can pick any subset of the sample space, right? And it's an event. So suppose that we're interested in the outcomes 2 and 3, and maybe yet another event consists of the outcomes 1 and 5. When an experiment is performed, only one of the possible outcomes will turn up. We know that to be true, right? When we roll a die, although there's 6 possible outcomes, on any one particular experiment, only one outcome will turn up. So suppose that we're ready now to perform this experiment. We've got the die in hand, we're going to roll it, and we get a 2. The question now is whether event A happened, given that the outcome that turned up is 2. So we will say that event A happened if the outcome that turned up is contained in the set A. So because 2 is contained in set A, we'll say that event A has happened. And because, again, the outcome that turned up 2 is contained in set B, we'll say that event B has happened as well. But 2 is not contained in C, so we will say that event C has not happened. And you see how we use the terms event and set almost interchangeably. But when we talk about the probability of something, we'll want to use the term event. And when we want to look at in a minute we'll see, what if we're interested in an event that both A, so we have event A here and event B. In a minute we'll look at what does it mean to study the event that both event A and B happen. When that happens, we'll have to go down to their definitions, which is in terms of sets and operate on sets. But for the most part, event and set will be used interchangeably. Okay, so that's it for introducing events. Very straightforward. And now we're ready to introduce some definitions. Well, I mean, we've already been introducing definitions, right? Sample space, event. But now we will introduce some definitions that help us relate sets. And the first one we'll want to introduce is what it means for set. What letter should I use? Let's do P. What does it mean for set P to be a subset of set Q? So we'll say that P is a subset, set P is a subset of set Q if and only if, should it be the case that X is any outcome or element of P, if that fact alone implied that X must necessarily also be an element or outcome of B, then that implies that P is a subset of Q. Yeah, so there are a few things here that are worth unpacking, I think, as we go through this at a first pass. The first thing is this operator, the if and only if. Notice that it consists of two conditions, if, only if, tied together by this AND, this logical operator. Okay, and then what's on the left side here and what's on the right side? Well, on the left of the if and only if operator is this expression, P is a subset of Q. And so if we were to draw a sample space, say this is a sample space, this rectangle, and so I got sample P here consisting of the points inside, and maybe I draw a set Q here consisting of the points inside of this other circle. So the way I've drawn them, P is not a subset of Q. Right, and then perhaps alternatively it could have been the case that if this is P, that in this Q, here P is a subset of Q. So P is a subset of Q will either be true or false. It's a Boolean expression. So let me choose a letter for this left side. I'll just choose L. So this expression P is a subset of Q is a logical expression. I'll just use kind of the variable L as a placeholder for that Boolean value, true or false. And on the right side we have another Boolean expression. So the right side will also be either true or false, and I'll just use the letter M to denote that Boolean value. So let's think about what it means to say that L, if and only if, M. So this if and only if construct, let's unpack that one just for a minute. So if, let's write some sentences here in English which will guide our thinking around it. So you live in France if you live in Paris. So you live in France is a Boolean expression here, and you live in Paris is another Boolean expression, denoted one left by L, one right by M, and there's an if in there, right? We're dealing now with this first if and only. So what does it mean to say that you live in France if you live in Paris? It means that you live in Paris is sufficient for you to conclude that you live in France. So in other words, M implies L. So the truth value of M implies the truth value of L. If M is true, L is true. If M is false, L is false. M is sufficient for us to conclude the value of L. Okay, now what about the second part, the only if? So let's write another sentence here. You can pass the course only if you take the final exam. Okay, so you can pass the course now is our L. You take the final exam now is our M, and they're connected by only if. So what does it mean to say that? So now we are saying that you taking the final exam is necessary for you passing the course. You cannot pass the course if you don't take the final exam. So in this case, what this says is that if you observe L, if you observe that, or if I observe that you passed the course, you must have sat for the final exam. So here L implies M. And notice that this first one here, right? If I just keep L on the left and M on the right, we have M implying L. That's what the first condition says, and the second one, L implies M. And they are connected by a system that the system stands for that and. So this if and only if has two directions, right? And left to right and right to left. And you can see that in the way we draw this operator. It has the two directions. Okay, so in our particular case, I'll just make a little bit of room. In our particular case, what are these two statements? These two directions, what do they amount to? Well, it says that if P is a subset of Q, then it must be the case that should you pick X to be an element of P, and I apologize, over here at the top, it should have been a Q. That should you pick X to be an element of P, it must necessarily also be an element of Q. So that's the left to right. And then what about the right to left? Well, this one says if we picked X to be an element of P, and if that automatically implied that X must also be an element of Q, then that implies that P is a subset of Q. Okay, so I spent quite a bit of time here unpacking this if and only if, but it's just one of those things that obviously will be used a lot, and I think there's a risk of missing some color if we're not comfortable with it. Okay. So we got this first definition in place. Let's do one more. What does it mean for two sets to be equal? So we will say that set P and Q are equal, sets P and Q are equal if and only if P is a subset of Q and Q is a subset of P. Okay, so let me just very quickly look at some Venn diagrams for these two conditions. Let's see if we get a little bit more intuition from it. There isn't a ton, but there's a little bit of intuition from the Venn diagram in these cases. So the first one, and I guess we'll do a separate drawing for the left side and the right side of each. So got 4 sample spaces ready. Okay, so let's look at this left side and the first definition. It says P is a subset of Q. So it means we've got to draw P and Q such that P is a subset of Q. So it says that if that's the case, that P is a subset of Q, then should you pick an X inside P, it will also be inside Q. That makes perfect sense, right? And the right side says that if you started with a set P and you picked X to be an element of P, if that alone automatically implied that X is also an element of Q, then the only way for us to draw that Q is such that P must be a subset of Q. So that's it for that first one, first definition. Now the second definition says what? There isn't much we can draw for the first one, P and Q to be equal. I mean, we know what that means. We'll have to draw P and Q to exactly overlap. But on the right side, let's just draw what it means for P to be a subset of Q. So let's set P here and a set Q. So P is a subset of Q. Now let's think about what other condition would need to hold in addition to the fact that P is a subset of Q for us to say that, be able to say that P is actually equal to Q. And notice that that other condition that we need to hold is that Q is a subset of P as well. Because when that happens as well, that will either expand P to Q or shrink Q to P so that they exactly overlap. And you know, and then when they do, of course, you know, P and Q would represent exactly the same set. Okay, so at times a Venn diagram can add a little bit of intuition, but as the authors make clear, you cannot rely on Venn diagrams for proofs. So just for intuition, or we can find when there is any to be found. Okay, 3 more definitions. Let's look at what it means for us to take the union of two sets. So if we had a set Y and a set W, the union of two sets consists of all the elements little x such that x is an element of the first one or x is an element of the second one. So notice what this says. It says that being okay, so here's the set Y and here's the set W. It says that for an element to be included in the union of sets y and w, it is sufficient that the element be an element of either. So therefore the union of two sets consists of the points that are in either set, and those that are at the intersection of two sets are both, so they are definitely also included in the union. Okay, so there's that. Now let's look at intersection. What does it mean to take the intersection of two sets? It means to select the elements that are included in both. So inclusion in both sets is necessary. Existence in both sets is necessary for inclusion in the intersection. So the sample space for intersection is, we've got y here and we've got w here, so it's only the points at the intersection of the two sets that will make it into y intersection w. Okay, so there's that, and one last definition here before we can go on and do some interesting things is that of a complement. So the complement of the set y consists of all the elements little x that are elements of the sample space, such that x is not an element of y. Okay. And the sample space for this is, here's the sample space, here's y. So let me redo this one. So y represents the point, set y consists of the points inside this circle. So then if we're interested in the complement of y, the complement of y consists of all the points in the sample space that are not in y. So there we go. Okay, so let's do one simple example to practice with these concepts, and then we'll get to some proofs, which is kind of the substance of this. The proofs in Theorem 114 is the substance of this section. Okay, so if we okay, so let's just look at example 113. Example 113. So this one says we just select a card at random from a standard deck and we note its suit. So the suit can be clubs, diamonds, hearts, or spades. So when we select a card, this card from the deck, we only note its suit and we discard any other information. So the suit is all we're interested in, and there are only 4 possible suits. So there are 4 possible outcomes. We put these in a set, and that's the sample space for this experiment. And then we're told that we are interested in a couple events. We're interested in event A, that the suit of the selected card is C or D, clubs or diamonds. We're also interested in event B, which consists of D, H, S, and we're also interested in, nope, that's it, only 2 events, but we are interested in what A union B is, we're interested in what A intersection B is, and we're also interested in what the complement of A is. Okay. So A union B, by definition, and so let me number these definitions. We've got 1, 2, we've got definition 3 there, 4, and 5. So by definition 3 of union, we're going to include in A union B the elements that are in either A or B. So what's in A, C, and D, and what's in B, there's another D, but like we said, existence in either set is sufficient to be included in the union. We already included D, and the set contains unique elements, so we're not going to repeat D, but then we will include the other elements of B, H, and S. So that's so these are the elements that are included in A union B. A intersection B will consist of the elements that are in both A and B, and that's just D. And the complement of A will consist of the elements that are in the sample space that are not in A. And so you see that what's in A, C, and D. So then what's in sample space that's not in A is just H and S. Okay, and then a couple more things are noted here. One is that, so we're said, notice that A union B is equal to the sample space. So, in other words, the sample space itself can be thought as an event. It's the event that, well, think about what a sample space is. It consists of all the possible outcomes. So then the event, which consists, the sample space, basically is the event that corresponds to the fact that something will happen. One of the outcomes will turn up. And if we were to take the complement of A union B, by definition 5, now we're looking for the elements that are in the sample space that are not in A union B, and there are no such elements, so this gives us an opportunity to define the empty set, or the set with no elements, and these are the two ways in which we can denote it. So the empty set is another legitimate event that we can be interested in, and we have a notation for it now. Okay, so we are ready now to move on to Theorem 114. So in Theorem 114, we're going to state 4 different laws that pertain to set operations, and as part of the theorem here, the authors prove only one of the laws, the distributive law, but as part of exercise 1.3, we're asked to prove the other ones, so I'll just prove all of them here as we go along. But first I will introduce them in order, and then I will prove them. So let's start with the first one, commutativity. Let me choose a different color that we don't have here yet. So A, commutativity. The names of the laws are not important, but it's important to know what we can and cannot do with sets. So if we had 2 sets and we union them, took A union B, what we would get is a set, and it's the same set we would get if we instead did B union A. I think this is perfectly intuitive. Right? I mean, we drew a sample space and we got set A and set B. A union B, it almost says that we're going to start coloring from left to right. B union A is the same thing. We're just going to color from the other side, right? It refers to exactly the same elements. Proving it, though, is not trivial. We'll do it in a minute. But an analogous result holds for intersection A intersection B. We get the same set if we do B intersection A. Okay, that's it for commutativity. Next is associativity. So for associativity, what we have is a a chain of sets chained by the same set operator, in this case union. So if we had this, let me just start by writing the same thing on both sides. And then if suppose we want to do this one first and this one second, we would get the same thing if instead we did that one first and this one second. And of course the way we denote it in math which one we do first is with parentheses. So so this is what the associativity law says, that if you have a chain of sets connected by the same operator, in this case union, it doesn't matter the order in which you do those unions. And an analogous result holds with intersections, perfectly analogous. Says doesn't matter if you did this one first, this one second, or this one first, this one second. In other words, if we put the parentheses like that, it doesn't matter. The order doesn't matter. Okay, so that's associativity. And next we will look at the distributive laws. Okay, see, distributive laws. So now we're mixing operators. So if we have A intersection with B union C, what happens is, the way I remember it, is that we distribute the operator that's in front of the parentheses to each set inside the parentheses. So we distribute an intersection to B, and we distribute an intersection to C, and then these are chained together by the operator operating inside the parentheses, and that's the union. And there's an analogous one with a union in front of the parentheses and intersection inside. And so now we're distributing the union. So we get A union B and A union C. And these are chained together by the operator operating inside, and that's the intersection. Okay, and so the same result holds if we had, more sets inside the parentheses. So I'll just show, let's say for this one, a more general expression. If we had A intersection with B, union C, union D, union E, it's the same thing, or the same concept will apply. We're going to distribute the intersection to each element inside, to each set inside the parentheses. So we've got intersection B, intersection A, intersection C, D, and E. Okay, and now these are chained together by the operator operating inside the parentheses, and that's the union. So, and there's an analogous generic version for that one, where inside the parentheses we'll have B intersection C intersection D intersection E, and you get the point of how it works. Maybe I should have mentioned for associativity too, that chain could be as long as we want. So we said that for associativity, the previous law, we said that A union B, A union B, union C, that it didn't matter which ones, the order in which we did these operations. So we said that this is true. If we added another one here, set D union with all of those, and should have made more room for it, and then we added set D on this side as well. Once again, it doesn't matter. So we could do this one we could put the parentheses here, meaning we're going to do this one first, this one second, and this one third. And here we can do whatever order we pick. Maybe we want to do this one first, and then this one second, and this one third. We'll get the same thing. So associativity says that if you have a chain, basically you have a bunch of sets held together by the same operator, union in this case. Doesn't matter which operation you do first. And the distributive law says that if you now mix operators and you have one operator in front of a chain held together by the other operator, then you basically distribute the operator in front of the parentheses to each set inside the parentheses, and they're chained together by the operator operating inside the parentheses. Okay, so there's that, and now on to the last law, and then we'll prove these and move forward from there. So so the last law is called De Morgan's laws. Okay. So in D, we've got the De Morgan's laws. So this says that if you had a chain inside the parentheses, so I'll do it with 3 elements right away, make things clear. And we took the complement of this chain, we will take the complement of each element, and they will be held together by the other operator than the one operating inside. So this is what we have for complement of a chain held together by unions. And then if we had intersections inside the parentheses, then we'll take the complement of each set, and they'll be held together by the operator other than the one operating inside the parentheses, and that's the union. Okay, so we've introduced these laws, but now let's convince ourselves that that they actually are true. And so finally we're able to start doing some math, right? Because up to now it's just been introducing definitions and some claims. This theorem is just a bunch of claims. We haven't proven anything. So let's start by proving commutativity. So commutativity, and I'll alternate between the unions and intersections because they're very analogous, and there's no need to do both. So this is what we're trying to prove. We're trying to prove that A union B equals B union A. So let's denote the left side here by P. So when we take the union of A and B, we'll get a set. So let's call that set P. And when we take the union of B and A on the right side here, we'll get another set. Let's denote that set Q. So we're investigating whether P equals Q. And from definition 2 above, you see that P will equal P will equal Q if P is a subset of Q and Q is a subset of P. Okay, so then the first thing we want to show is that P is a subset of Q. And how can we do that? Well, from definition 1, P is a subset of Q if the right side is true. Okay, so then we'll want to look at this right side. And this right side starts by assuming this first part here, that we're letting X be an element of P, and we want to show that in that case X is automatically an element of Q. Okay, so let's do that. Let's let X be an element of P, and then let's just flush out what P is. That means if X is an element of P, then X is an element of A union B. Okay, and then from definition 3, we see what it means for X to be an element of A union B. It means that X must be an element of the first one, or X an element of the second one. Okay, and you know, the order in which we write these doesn't matter, right? So we can say, okay, X must be an element of B, or X must be an element of A. And you know, now by the same definition 3, but going from the right to left, we can say that X must be an element of B union A. And notice that B union A is exactly Q, therefore X must be an element of Q. Okay, great. So what we have shown here, we have assumed that X is an element of P, and we have shown that that necessarily implies that X must also be an element of Q. So we have shown this right side here in definition 1. Therefore, what we've accomplished to show that P is a subset of Q. Okay. So we finished this part in definition 2, that P is a subset of Q. Okay. Now we need to show that Q is also a subset of P. And how do we do that? By definition 1, we see that we'll need to let X be an element of Q, and we'll want to show that that implies that X must be an element of P. Okay, so if X is an element of Q, let's unpack what Q is. Well, that's B union A. Therefore, X must be an element of B, or X must be an element of A. Again, the order in which we write these doesn't matter, so we can say X is an element of A, or X is an element of B. And that means then by definition 3, going from the right to left, that X is an element of A union B, and notice that A union B is exactly P, so therefore X is an element of P. Okay, so we started by assuming that X is an element of Q, and we've shown that that implies that X must be an element of P. Therefore, we've shown that P is a subset of Q. Okay, so now we're done with this side here in definition 2. So we've shown that P is a subset of Q, and we've shown that Q is a subset of P. Therefore, we have shown that P is equal to Q, and we are done with this proof. Okay, so that's commutativity. Now let's look at associativity next. See how we prove that one. In all of these proofs, you see that we're going to be unpacking everything to basically the ors and ends, and then backing it back up. It may not be so clear yet, but let's do a couple more and then you'll see what I mean by that. So for associativity, we want to show that A unioned with, let's do the intersection now because we just did union. Let's do the intersection. A intersection with B intersection C. We want to show that that's equal to A intersection B intersection C. Okay. So how would we do that? Well, once again, what's on the left is a set, we'll call it P. What's on the right is a set, we'll call it Q. So when are two sets equal? By definition 2, we have to show that P is a subset of Q, and then we have to show that Q is a subset of P. And by definition 1, when is P a subset of Q, we have to show the right side of definition 1 to be true. So same thing, so we're trying to show that P is a subset of Q, and we'll start by assuming letting x be an element of P. We want to show that x must necessarily also be an element of Q. So let's unpack what P is. That's what P is. Okay. And so now let's unpack what this intersection is. From definition 4, we see that this means that x is an element of A, and x is also an element of B intersection C. Okay. Now there's one more thing to unpack. We have to unpack what this intersection is, and we see from definition 4 again that x must be an element of B and x must be an element of C. So you see again we've gone down as far as we can to this level of ands and ors, and so this parenthesis here plays no role, right? We could get rid of it and we could place it, you know, wherever we want, and so we could place it here, in which case now what have we got? What's inside the parentheses now, by definition 4, going from right to left, says that x is an element of A intersection B, and then we got and x is an element of C. Okay, and then by definition 4 again, going from right to left, we see that x must be an element of the intersection of the two sets. The first set is A intersection B, the second one is C, and then we said that x must be an element of the intersection of these two sets. And that's what we've been trying to show, that's exactly our Q. So we've shown that x must be an element of Q. Okay, so we've accomplished showing that P is a subset of Q, and you see now that okay, so what's left is we have to show that Q is a subset of P, but you know, I'm not going to write it out because it's exactly the same logic. It's just we're going to start at this end, and we're going to be walking from here to, you know, to this end, right? Okay, so that's proving associativity. Next, let's look at distributive law. So distributive law and so let's pick, I mean, it doesn't matter which one we pick, let's just take A intersection with B union C, and we want to show that that is equal to, we know how that works. We distribute an intersection to each set inside the parentheses, and we connect them with the operator that's inside the parentheses union. Okay, so how do we prove that? Well, exactly the same process. We're looking to show that set P is equal to Q, right? So first we got to show that P is a subset of Q. So exact same process. So we'll let X be an element of P. Then we unpack what that means. X must be an element of A intersection with B union C. Okay, and then let's unpack what this intersection means. From definition 4, it means that X must be an element of A, and X must also be an element of B union C. Now let's unpack what that union is. So what does it mean that X is an element of B union C? By definition 3, it means that X must be an element of B or X an element of C. So now we got an AND and an OR. And so what this says is that X is definitely an element of A, and in addition to that, it's also an element of B or C. So this can be written differently. We can say that X is an element of A and X is an element of B, or X is an element of A and X is an element of C. Right, so this may just require you to pause for a second, make sure that this makes sense. Right, so this above statement here said that X is definitely an element of A, and in addition to that, it's an element of either B or C. And that's what we've written here. The possibility, the case in which X is an element of A and B, and then the case that X is an element of A and C, and they're connected by an OR. So now we just use, so you see in what's inside the parentheses here, we're just going to use definition 4 from the right, going from right to left. So what's inside the first parenthesis just says that X is an element of A intersection B, right? And then there's an OR, and what's inside the second one says that X is an element of A intersection C. Okay, and then we're going to use definition 3, going from right to left, and then we'll say that X must be an element of the union of these two sets. So let's just write it out. X must be an element of, let me write the first set, let me write the second set, and we said that X must be an element of the union of these two, and that is exactly Q. Therefore, we've shown that X is an element of Q. Great. So you see, we've shown that P is a subset of Q, and as you know, so we're done with that. You would still have to show that now Q is a subset of P, but again, it's not interesting to write it out at this point because it would be just going from this direction and this direction, right? We're gonna let X be an element of Q and show that it's also an element of P. The novelty in that second part here is minimal, so I won't cover it, but you'd have to do it for completion to show that P at the end is equal to Q. Okay, so we are done with distributive law. The last one left is the De Morgan's law. I lost my bar there. Bring it back in a minute. Okay, De Morgan's law. So this is D. De Morgan's law. We got A union B. The complement of that is equal to, we take the complement of each, we connect it by the operator other than the one that's inside the parentheses. Okay, so again, this is P, this is Q. How do we show that two sets are equal? We've got to set that, and we show that they're subsets of each other. And so let's start with the first one. We want to show that P is a subset of Q. How do we do that? We let X be an element of P. We unpack what that means. X must be an element of the union of, well, so I just wrote what P is, A union B, and the complement of that. Okay, so now by definition 5, what does it mean that X is an element of the complement of a set? It means that X must be an element of the sample space. Okay, I'll skip that part because it's understood. I just wrote it there for completion. Okay, as such that X is not an element of the set we got here. So X is not an element of the set inside the parentheses, which is A union B. Okay, so so if X is not an element of A union B, and we know how unions work, so we can draw a little Venn diagram. So if we have A here, B here, let's draw the union. This is A union B, so I highlighted A union B, and we're told that X is not an element of A union B. Okay, well then X is not an element of A, and X is not an element of B, right? Okay, and so X is not an element of A. By definition 5, going from right to left, that can be written as X is an element of the complement of A. Now we've got an and X is an element of the complement of B. Okay, and then by definition 4, going from right to left, we have this and there, so that means now that X is an element of the intersection of these two sets. Okay, and that's what we've been after. So we've shown that X is an element of Q. Okay, so we started by letting X be any element of P, and we've shown that it automatically implies that X must also be an element of Q. Therefore, we've shown that P is a subset of Q. Okay, so we did the first part. As before, you'd still have to show that Q is a subset of P, but it's done exactly the same way. Well, not exactly the same way, but there's no novelty in that. You'll just be going from this direction to that direction, and once you've shown that, then you will have shown that P is equal to Q. Okay, so these are the laws presented in Theorem 114. We're done with those, and now let's introduce what it means to take the union and intersection of infinitely many sets. Just make some room. Okay, so the union of sets AI, where I goes from 1 to infinity. So we're taking the union of infinitely many sets. But we know how unions work, and we said that membership in any one of the sets is sufficient for you to be included in the union of these sets. Therefore, it will consist of the elements little x, and for x in the sample space, of course, such that X is an element of AI for some I. That's exactly what we said. There must be at least one AI that X is a member of for it to be included in the union of all the AI. And the intersection of the sets AI, as I goes from 1 to infinity, we said that now membership in each set AI is necessary for inclusion in the intersection. Therefore, X is an element of the sample space such that X is an element of AI for all I. So nothing new here, just extended from the definition from union of two sets to a union of infinitely many sets. And there's an example that we can work with. So we're told that if we picked our sample space to be the set between 0 and set of real numbers between 0 and 1, open at 0 and close at 1. And if we defined AI to be the closed set that goes from 1 over I to 1, and now we're asked what the union of AI as I goes from 1 to infinity looks like, and with the intersection of AI as I goes from 1 to infinity looks like. So, I mean, the hard part here, I think, is just understanding given what we're asked. So, you know, what is this AI business? It's a little contrived, this example, and so let me. I need a little more space for these definitions. So I guess the way this question really starts is by saying, suppose we were interested in a bunch of events or sets. Set A1 that we're interested in is, you know, I'm plugging, you know, a 1 for this I here, and that would be the set that goes from 1 over 1 to 1, and that's just the element 1. So suppose we're interested in this set. Now suppose we're also interested in set A2, which plugging now 2 for I would go from 1/2 to 1, and then suppose I'm also interested in set A3 that goes from 1/3 to 1, and you know, set A100 that goes from 1 to 100 to 1, and so on. Okay, so we're interested in all these sets where we let I be an increasingly larger number, and then we're interested in studying the union of these sets and the intersection of them. Okay, well, you know, so I think if we looked at these kind of graphically, A1, and so if this is the interval between 0 and 1, so it's going to be 0 and 1, and so now the set A1 corresponds to just point 1, the point of value at 1. A2 would go from 1/2 to 1, right? So cover this interval. A3 goes from 1/3, maybe somewhere there, to 1. So cover that. Okay, and A100 would go from 1 over 100 to 1. So, okay, and then as we let I go to infinity, so let's see what that looks like. How do we want to write this? The limit of AI, let's study that, as I goes to infinity. What does that look like? Well, it'll be an interval that will consist of what will be the limit of 1 over I as I goes to infinity. So this is the left side and goes to the right side of 1. Okay. Okay, and so what is the limit of 1 over I as I goes to infinity? Well, that's 0. Sorry, but now So when we moved to this limit here, and now that we're thinking about it, my tool's wrong. So now if we're thinking about this limit, as I goes to infinity, this left side will go to 0, but it will never attain 0. So then we have an open parenthesis on the end, and so then we get the interval from 0 to 1, where it's open at 0 and closed at 1. Okay. That's just what kind of think of it as A with an index of infinity would look like informally. Okay, so what's in the union of all of these? We said that to be included in the union you have to be an element of at least one of the sets AI. So we can take the biggest one in this case, which is kind of the A infinity, which covers the entire sample space. So the union of all of these will just be this set between 0 and 1, which is exactly the sample space, open at 0 and closed at 1. Okay, and what about the intersection? So now we're looking for the elements that are elements of every single set, and so we can look at the smallest one in this case, which is A1, which just contains the element 1. So the intersection of all of these will just contain the number 1. And that is it. Okay, so just a couple more things now. We'll introduce the what it means for one set to for two sets to be disjoint, and for two or more sets to be pairwise disjoint, and we'll look at a partition, and then we'll be done with this section. Okay, so so two events A and B are disjoint or mutually exclusive if A intersection B is equal to the empty set. So in other words, so let me write here, disjoint, and mutually exclusive will be used interchangeably. So two events A and B are disjoint if A intersection B is equal to the empty set. And so disjoint sets have no elements in common. So if we drew a Venn diagram for two disjoint sets, the sets will not overlap at all. So here's A. So for me to draw now B, such that A and B are disjoint, I just need to draw any set B that doesn't have any points in common with B. So A and B are disjoint. And what if now we had three sets, A, B, and C? We need now a concept for whether three sets are kind of like disjoint, right? So when we have more than two sets, we'll talk about whether three sets A, B, C, so A, B, and C are sets A, B, and C pairwise disjoint. That's the question. And pairwise disjoint, this pairwise says that you will look at each pair. So we'll look at A and B, then we'll look at A and C, and we'll look at B and C, only 3 pairs. So A, B, and C will be pairwise disjoint if these 3 pairs, so if A and B are disjoint, A and C are disjoint, and B and C are disjoint. So let's see if what we've drawn here in this sample space, if A, B, and C are pairwise disjoint. Are A and B pairwise? Are A and B disjoint? Yes, A and B do not have any elements in common, therefore they are disjoint. Are A and C disjoint? Yes, A and C do not have any points in common, they are disjoint. What about B and C? B and C, however, do have this overlap here, right? So therefore, B and C are not disjoint, and therefore A, B, and C are not pairwise disjoint. So you see now that in order for us to draw a sample space with 3 or more sets, so we can take a bunch of sets, so I've drawn 5 sets. Because no 2 of them have any elements in common, these 5 sets are pairwise disjoint. And that's it. That's all there is to it. But now look at this. Look at this picture here. We drew a sample space, and we drew 5 sets inside of it. And there are still elements in the sample space that are not included in any of these 5 sets. But now imagine that what's left in the sample space that's not in these 5, basically the complement of the union of these 5 sets, is the 6th set. So now we have sets 1, 2, 3, 4, 5, and then what's left in the sample space that's not in the other 5 is set 6. So this will prove to be an interesting way to kind of partition the sample space, and you see the name partition comes already kind of logically seems to belong there. And so formally we'll refer to a partition of a sample space as, make some room here. So definition 116 says A1, if sets A1 and A2 and so on are pairwise disjoint. Okay, so we got our 6 sets here that I drew, and they are pairwise disjoint, sets 1, 2, 3, 4, 5, and 6, right? No 2 of them have any elements in common. Okay, and if their union is the sample space, and it is the case, right? Because we've got sets 1 through 5, and set 6 has been defined as the point in the sample space that are not in the other 5. So their union is the entire sample space. Then these, in the definition, sets AI form a partition of the sample space S. In our case, the sets 1 through 6 here form a partition of the sample space S. Partitions will be quite important in a lot of what we'll do in probability. Notice that there are many different ways to partition a sample space. So if we looked at the experiment of rolling a die, where the sample space consists of the numbers 1, 2, 3, 4, 5, 6. What's one partition? One partition would be, I'll denote it by P1, would be what? The sets 1, 2, 3, 4, 5, and 6. right? So that's one partition. Another partition would be taking 1, 2, 3, and 4 together, and then 5 and 6. Right, so this is a set, one set, it's another set, yet another set, 3 sets. These 3 sets are pairwise disjoint. Yes, they have no elements in common, and their union is the entire sample space. Yes, their union covers the entire sample space. In the second example, this is one set, this is another. They have no points in common. That's right, they're pairwise disjoint, and their union covers the entire sample space. It sure does. Okay, that's all for section 1.1, and I will see you in section 1.2.